Hey everyone, Mr. Fransky here. This is the last section we're going to do in Chapter 7 at 7.4, Length of a Curve. And this seems like a pretty simple idea, and it's one of the things that, I remember when I first learned it, I was like, why haven't I ever learned this or thought about it before? Because it seems like a pretty logical question. So how long would you guess the sine wave is, like the length of the actual line from 0 to 2 pi? So like from here to here, how long would you guess that that line is? Well, think about it for a second. I don't know, 2 pi is like what, 6.3-ish, about, maybe? So the length of the line from here to here along the axis, that's a length of 6.3. So it goes up and down a little bit. So I don't know, make a guess right now. We're going to be able to find this out later. But see if you can guess, I don't know, approximately what the length of that is from 0 to 2 pi, and we'll see what happens with it. But this is a question that you can't answer without calculus. And that's because, think about it, it's changing direction all the time, right? So like, unless you had a straight line, right? So if you had like a linear function, you could find the distance between 2 points by using the distance formula. But for this, it's like we'd have to use an infinite number of distance formulas that are infinitely short. Well, that sounds exactly like what integrals do, right? They add up a bunch of little values. So let's see if we can figure this out. So we're going to derive this. This is definitely a proof-hat equation. So if you don't want to write this down, that's just fine. If you want to double the speed of the video, you can do that. But it's interesting, and it's important that you can follow this proof, but it's not something you'll have to replicate. So what we're going to do is we're going to start with this kind of idea that we have a curve that looks something like this. Okay? And we're going to do exactly what we said. We're going to partition it into a bunch of pieces. Okay? So we're taking lots of little distances. We're going to make these all straight lines. Okay? So what we obviously want to do is make these distances as short as possible, right? But what I'm going to think about is kind of each one of these is creating a triangle that has a delta x and a delta y. Okay? So each one of these triangles has a delta x and a delta y, and really what determines that delta x and that delta y is the slope of the function at that point. Well, the slope of a function is the derivative, so this is going to have something to do with the derivative. So if we think to Pythagorean theorem, the length of each one of these, right, the length of each one of these kind of hypotenuses of the triangle is going to be the square root of delta x squared plus delta y squared, just because we have Pythagorean theorem. So this guy right here, so if we have delta x, we have delta y. This guy is going to be the square root of delta x squared plus delta y squared plus delta y squared. Right, because delta y squared plus delta x squared equals the hypotenuse squared, so it's the square root of the sum of the squares. Excuse me. So really what we want to do, if we want to go from A to B, so we're going to find the distance, or the curve length from A to B, what we want to do is we want to add up the sum of the delta x squared plus delta y squared, okay, on this interval from A to B as delta x goes to 0. Right, well, those delta x's to get as small as possible, because then the straight lines are essentially going to be the same distance as the curve, the smaller those delta x's get. So adding all of these up isn't hard as long as they're actual values. But the problem is, like, if we want to use an integral to do this, integrals usually have a delta x at the end. Okay, so the problem here is integrals have that delta x at the end. So it's like sum of a bunch of stuff, and the delta x is at the end. We don't have that. So what we're going to do is we're going to force it there. Okay, so we're just going to do this. We're going to do square root of delta x squared plus delta y squared. So I'm going to multiply by delta x. I'm also going to divide by delta x. So I haven't done anything. I've just multiplied by 1. I just multiplied and divided by delta x. And now we're going to do, so now we have the delta x at the end, and we're going to see if we can make this inside part look a little prettier. So what I'm going to do is change that delta x on the bottom to the square root of delta x squared, right? That's still delta x. And now we have the square root of the top, square root on the bottom, so we can make that one expression. So we have the sum of the square root delta x squared plus delta y squared divided by delta x squared, delta x at the end. Now we can split this up, right? Some of you call it butterfly, some of you say if it's a heart, break it apart, but however you want to do it, this is the sum of the square root. Delta x squared over delta x squared is 1 plus delta y squared over delta x squared, delta x at the end. All right. And this delta y squared over delta x squared, we can just make that delta y over delta x quantity squares. This is the sum square root of 1 plus delta y over delta x squared, delta x. Now you might be able to see where this is going. Delta y over delta x, change in y over change in x, that's the slope. right? That is the slope of this line right here, okay? And as delta x turns into 0, we kind of think about mean value theorem. So we think about one of those triangles here. All right. So this is delta x, this is delta y. So mean value theorem tells us as long as the curve is smooth, so that's going to be our requirement for determining curve length. As long as the curve is smooth, somewhere between, let's call this little a and little b, somewhere between a and b there is a c value where the slope of this line, if I had drawn it better, slope of this line is equal to the slope of this line. And what's happening is delta x is turning into 0. So delta x is squeezing smaller and smaller and smaller and smaller. And so what's going to happen is there are going to be fewer and fewer choices for where the c is going to be. And it's going to turn out to be the only point that's left, right? This is going to get so small that the only point that's going to work is going to be the same point that fits into that delta x. So what happens is this guy right here, because the derivative is equal to the slope, that's just going to turn into the derivative. Okay, so really what this becomes, so as delta x goes to 0, so we had the sum of the square root of 1 plus delta y over delta x quantity squared dx is going to turn into the integral of the square root of 1 plus, this is just going to be f prime of x squared dx. Okay. And that turns out to be our formula. Okay, so this is our curve length formula right here, and let's get that kind of a little bit more formal. Okay, so here's our curve length formula. So as long as f of x is a smooth function, okay, so long as f of x is a smooth function, that means that it's differentiable on the interval AB wherever you're trying to find the length. Remember, the quickest way to find out if something is differentiable is to take the derivative and see if there's any values you plug in on the interval that don't work nicely. So if there's an x on the bottom, you can put 0 in, right? Stuff like that. Okay, so f of x is a smooth function. Then the curve length on AB is L is equal to integral from a to b square root 1 plus f prime of x squared dx. So really this is the only important thing to write down today, is knowing this formula. Okay, or if you do it in terms of y, so let's say that this is x coordinates, so let's say the y coordinates are CD. So sometimes this is a way to get around the whole smooth thing. Sometimes like x will have a vertical tangent or something, you can do it on y instead. So if the y values go from c to d, you can integrate from c to d, square root of 1 plus f prime of y squared dy. Okay, from y quantity squared. So let's find out about that sine function. Okay, so let's go back to that sine wave. So what we want to do is the integral from 0 to 2 pi, 1 plus, square root of 1 plus the derivative of sine x squared, whoops, I'm doing this in more steps than I would normally do it, but that's okay, dx. So that is the integral from 0 to 2 pi, square root of 1 plus cosine squared x dx. Now there's no nice trig formula to combine this. I wish there was, but we're going to have to go to a calculator to be able to do this. I think I've got mine queued up here. Let's see if we can find it. There it is. So I'm going to do the integral. So menu, calculus, integral, 0 to 2 pi. Pi is next to the h. There it is. Square root is control square. There it is. 1 plus, so I'm going to do in parentheses, cosine of x, and then close parentheses and square it. I think your calculator supports putting the square after cosine, but this I know is going to work. It's cosine times cosine, dx. Control enter. 7.64. So maybe that was your guess. That's not a whole lot bigger than the 6.3. That's just the straight line. Okay, but that's 7.6403 is probably how I got that. 7.6403. All right, so that's the length of the sine wave from 0 to 2 pi. Not too bad if you have a calculator, right? You just have to be able to find the derivative, square it. Don't forget the square. That's important to say, I think. Don't forget it's f prime of x squared. So often, and this is usually how AP gets you on multiple choice questions. They just get people for not squaring their derivative. Okay, so it's the f prime of x squared, and then plus 1, square root, integral from a to b. Cool. All right, so why is this necessary or useful? So a few things that I can think of. You guys all have Google Maps on your phone. I know I've seen it. Length of a road, right? To find the length of a road on a map. This is super important. You can just fit a curve to the road and you can be able to find the length of the function. So calculating distances from place to place using length of a road. Finding surface area. So like if I took the sine wave and rotated it around this line, I want to know the surface area of the resulting solid. It would be the length of the curve multiplied by 2 pi r. We're going to do one example like that at the end. That's not something that AP requires you to know, but it's kind of a cool thing to be able to do, and there's a simple function that works out pretty nicely. So all kinds of applications to using the length of a curve in art, in geography, and in construction and engineering as well. So knowing the length of a curve, very, very important. All right, so let's try one by hand. There are not a lot of by hand examples because the formula is so complicated with a derivative that's squared, and then you add 1. How do you get the square root to be a nice function to be able to integrate it? So there are not a lot of these. There's like one on Khan Academy and then this one, and there are not a whole lot of others. So let's see what we can do. Find the length. Notice the coefficient here is messy because it has to be able to make all this work out. So find the length of this function on the interval 0, 1. Okay, so it should be integral 0 to 1, square root of 1 plus f prime of x squared dx. So f prime of x, let's find. So f prime of x here, the 3 halves is going to come to the front. So 3 halves times 4 root 2 over 3. X now to the 1 half, right, because we subtract 1. The minus 1 goes away because it's a constant. So let's see if we can clean this up a little bit. The 3's cancel. 4 over 2 is 2 root 2 times root x. Okay, so that's our derivative. So we're going to square that in our integral. So the integral 0 to 1, square root of 1 plus, if we square this, so if we square this entire thing, 2 squared is 4, root 2 squared is 2, root x squared is just x. So it looks like we'll have 8x underneath there. 1 plus 8x dx. Looks like a good candidate for u sub. So u is 1 plus 8x, and du is going to be 8 dx. So we need an 8 dx, which means we need a 1/8 out front. So this is 1/8 integral, changing over to u land. 0 becomes 1. 1 becomes 9. Those are nice square rootable values. That sounds about right. Then we have u to the 1 half, just root u, du. Okay, antiderivative of u to the 1 half, u to the 3 halves times 2/3. So you have 1/8 times 2/3 u to the 3 halves from 1 to 9. Pull that 2/3 out front. 2/8 is 1/4, so this is what, 1/12. So I have 1/12 times u to the 3 halves from 1 to 9. Okay, so plug in 9 there. Square root of 9 is 3, cubed is 27. So I have 1/12 times 27 minus 1. 26/12. Or reduce that, let's see, 13/6. And there's your curve length. Okay. Now, I should have checked this initially. Is this a smooth curve? Well, let's check out the derivative. 2 root 2 root x. So root x is okay all the way between 0 and 1. There's no issues there, no dividing by 0 or anything like that. So you have a smooth curve. All right, let's try another one. So this time, calculator is going to be okay, but it's a little tricky because of that whole idea of checking to see if we have a smooth function. So if we have y equals cube root of x from -8 to -2 to 8, 2. And also as kind of a hint, when they give you the y coordinate, you might have to change variables. So let's see what's going on here. So this is x to the 1/3 power. So the derivative is 1/3 x to the -2/3. That is 1 over 3x to the 2/3. There's an issue between -8 and 8. Right? 0 is included in there, so this is not smooth in relation to x. But what we can do, if you know cube root of x kind of looks like this. The problem is that you have a vertical tangent at 0. That vertical tangent at 0 is what's creating a non-differentiable function at that point. But what we can do is just put it in terms of y, because like x cubed looks like this. X cubed is smooth all the way through. So if we think about this in terms of y, it's basically like taking it and flipping it over the line y equals x, and creating this function. So if we do this in terms of y, there's no issue. So if you have a problem with a vertical tangent, You can just switch it over to y, and it's going to work out. So let's do that. So if we right here, we have x equals y cubed. Now we just go from -2 to 2. So we're using y values. So we integrate -2 to 2, square root of 1 plus, derivative of this guy is 3y squared dy. So that is integral -2 to 2, square root of 1 plus, what is that, 9y to the 4th dy. So you can see here, this is not going to be able to do by hand. We're going to have to go to a calculator for this one because we can't undo that y to the 4th on the inside. There'd be some messy chain rule stuff happening. So let's see if we can figure this out. So I'm just going to grab this, put in our values now. So we're integrating from -2 to 2. 1 plus 9y to the 4th. Let's see if we can get that in here. So we have 9y to the 4th power dy. Control Enter. 17.2606. There we go. Okay. So as you can see, not too bad. A lot of this is just plugging things into a calculator. Let's check out another one that's kind of interesting. So find the length of y equals x squared minus 4 absolute x. Ooh, that absolute. I know that scares people. Minus x on -4 to 4. So at 0, this is somehow going to change, right? So I think the easiest way to think about this is as a piecewise function. Should be getting comfortable with being able to change that absolute x to a piecewise function. So if x is positive, if x is greater than or equal to 0, then this is just 4x, right? So minus 4x minus x, that's x squared minus 5x. If x, however, is less than 0, this becomes a negative x. So I have positive 4x minus x, so that's going to be x squared plus 3x. Okay, so we have kind of two different functions here going on. So you factor out the x in the top one. Our zeros are at -3 and 0. So the first one is a parabola with zeros at -3 and 0. Something like this. And the second one has zeros at 5 and 0. So 5 will be over here somewhere. So that's going to be a parabola of something like this. So we kind of have this like double bump parabola. Okay, so it has a parabola that comes in like this, then it changes to a different parabola. So we know the length from -4 to 4. So it's not differentiable the entire time, but what we can do is we can just section it. So we go from -4 to 0, and then from 0 to 4. So we just find the length of the two different parts. So let's see here. So we have to find the derivatives. So the y prime, piecewise, is going to be 2x plus 3. And that's a 3, I promise. And then afterwards, it's going to be 2x minus 5. So to find the length here, it's going to be the integral from -4 to 0 of the first function. So square root of 1 plus 2x plus 3 quantity squared, because we square the derivative, dx. Then we add to that the integral from 0 to 4, the square root of 1 plus quantity 2x minus 5 squared. There we go, dx. Now, I would just take this and go straight to the calculator. And I'll let you give that a shot. I'm actually not going to show this one because it's just kind of a plug and chug. It ends up being about 19.56. Okay. Hopefully I wrote that down correctly and I actually did my calculator correctly before, but you can give it a shot. Alright, so now as promised, I got one more example with a surface area problem. This is a really cool surface area problem, and it actually ends up, the math ends up working out so nicely. So I hope that you'll watch it, but I don't require you guys to know how to do surface area problems, but it's pretty cool, so let's check it out. So we got the surface area of the solid created by revolving the region between x equals -2 and x equals 2, bounded by y equals root 9x minus x squared. That's a circle with a radius of 3, so -3 to 3, something like this. Okay, we're only going from -2 to 2. So we're kind of cutting it off at this point. So we're only using that kind of top little bit right there. So it'll look kind of something like this. Okay, if you rotated that around the x-axis, you're going to basically create like a bead, right? So rotate around the x-axis is going to kind of create this kind of a solid. Okay. Cross sections that are circles, right? We don't really care a whole lot about that. I'm going to erase that because it's getting in the way of my words. Okay, but this is what our function looks like, just from -2 to 2. And what I want to know is what is the surface area of that solid going to be. So imagine just taking this line, rotating it kind of through the air, and it's going to create this kind of shell shape, right? A shell shape. And the problem is though, like usually when we like rotate this thing around, we usually think about this as being flat, like a rectangle. Now I'm actually thinking about using a little bit of a curve. So each kind of point on this that rotates around is going to be, there's going to be a 2 pi r, kind of like we did with the shell method, right? Shell method had that 2 pi r thing because that's the circumference of the circle. But what happens is it's just a little bit angled. So when it kind of sweeps through the air, we're not sweeping just a point through the air, we're sweeping kind of this angled thing through the air. So for each one of these little pieces that goes around is going to be 2 pi r, but the radius is the height of the function. So 2 pi times the height of the function, which is root 9 minus x squared. And then times this idea of this little itty bitty curve length. So that's going to then be times the square root of the 1 plus f prime of x squared. Okay, and then we're going to integrate this from -2 to 2. So, a little bit weird conceptually, but this is how you always do surface area problems. You do 2 pi times the radius, which is the height of the function, and then you multiply by that derivative thing squared plus 1 square root. So, let's see if the math works out as well as I remember it. Let's give it a shot. So we have 2 pi, integral from -2 to 2, square root of 9 minus x squared, times the square root of 1 plus the derivative of this guy. So let's say this is 9 minus x squared to the 1/2. So the derivative is going to be 1/2. Let's put this all in here. So 1/2 times 9 minus x squared to the -1/2 multiplied by derivative of the inside function, which is -2x. That whole thing squared. dx at the end. So we're going to write that a little prettier. So we have 2 pi, integral -2 to 2, square root 9 minus x squared, times the square root of 1 plus, let's see, not going to square this quite yet. We're going to make this look a little nicer. The 2's cancel, thank goodness. So we have negative, let's see, x over square root of 9 minus x squared, that whole thing squared, dx. So when we square this, the x will be squared on the top, the negative will go away because they're just squaring the whole thing, it'll be positive. The bottom, that square root's going to go away. So let's say we have 2 pi integral, -2 to 2, square root 9 minus x squared, square root 1 plus x squared over 9 minus x squared, dx. So I'm going to take that, we're going to go to the next slide. I've got another blank one ready to go here. So let's see here. We have a root here and a root here. When you have like root x times root y, you can combine those to root xy. So that's what I'm going to do here. I'm going to combine these to have a multiplication on the inside of this integral. So we're going to have 2 pi, integral -2 to 2, square root of 9 minus x squared, times 1 plus x squared over 9 minus x squared. dx. Yep. So now what I'm going to do is I'm going to take this quantity and distribute it in here. Yep. So this is 2 pi, integral -2 to 2, square root of, so 9 minus x squared times 1 is just 9 minus x squared, plus now 9 minus x squared times this. Ooh, look, those 9 minus x squareds cancel. So it's just x squared. Check this out. How beautiful is that? What happens to the x squareds? They cancel. So this is the square root of 9. What's the square root of 9? 3. So we have 2 pi integral -2 to 2, square root of 3 dx. Just not square root of 3, just 3. Gosh. What are we going to do with that 3? Pull it out. This is 6 pi integral -2 to 2 dx. So that is 6 pi times x from -2 to 2, which is 6 pi times 2 minus -2, which is 4 times 6 pi, it's 24 pi. Beautiful. I love how simple that integral becomes. And from being so messy, I mean, this whole mess right here to turning into just 3, that's pretty cool. All right. So that's all I've got. Hopefully you found curve length kind of interesting. The derivation of it I think is kind of cool. There will definitely be a question about this on the test, and AP always asks usually a multiple choice question about this. I've seen some free response, but it's usually multiple choice. That's it. Love you guys. That's why I'm here. Have a great day.